Versal ACAP devices usher in a new architecture built around an updated programmable logic fabric, ARM cores, hard IP for memory controllers and high-speed communications, plus the new AI engines and network on chip. This new architecture is built using 7nm process technology and packaged in 4th generation stacked silicon interconnect. Versal designs are developed using the Vitis toolflow. If you previously developed or debugged FPGA designs in Vivado or even the older ISE tools, then you're probably familiar with the Integrated Logic Analyzer, also known as ChipScope. Today's topic is how can that Integrated Logic Analyzer be utilized to debug Versal designs, specifically those incorporating the new AI engines in the Vitis flow. I'm going to do a quick run-through showing the ILA running on a Versal target board. The project is already built and ready for hardware debugging, so the first step is to launch Vivado and open the hardware manager. Next, connect to the target board. We'll go into more detail on that later. And note that it finds the parts on the board, including a Versal VC1902. When the hardware project containing the ILA was built, a probes file with .ltx extension was generated. Selecting the Versal part, then going to its properties box and specifying that probe file will open the logic analyzer after refreshing the hardware link. You can then go to the tab and open the logic analyzer. Now that we're connected to the target, the ILA can sample the selected signals. The first impression here is that most of the sampled interfaces are inactive. The second observation is you must zoom in quite a bit to see data transitions. Decreasing the sample depth can speed up transfers and make the display more manageable. Casting a wide net is fine initially, but it's generally better to sample less and be more selective on where you look. With that goal in mind, we'll set up trigger conditions to monitor 4 of the inactive buses. To that end, we'll set the trigger on T-ready, watching for assertion as a logic 1. Combining these 4 trigger conditions as a Boolean OR will trigger the analyzer if there is bus activity on any of these buses. To position the trigger condition near the start of the sampling window, we'll also set the trigger position in window to a lower number. Rerunning the logic analyzer, then checking the status shows waiting for trigger. So we can deduce that there is really no bus activity on the 4 monitored interfaces. We'll leave the ILA in a waiting state for now. Now, the point of this demo is not to show you how to use the ILA, but rather to show that the ILA in the Vitis toolflow for Versal parts drives very much like it did in Vivado for FPGA designs. There are some differences though, and that's where we're going to focus for the rest of this video. The key differences would be the number of compute domains, the different hardware for the host-target interconnection, and cross-domain debugging strategies. So let's start talking about what's new by focusing on the compute domains. The Versal ACAP has 3 processing domains: the programmable logic fabric, the processor system, and the AI engine array. Hardware debugging must consider all 3. As a simple example of crossing domains, let's reconsider our logic analyzer, which is still waiting for trigger. The AI engine domain is typically under control of the processor domain. So to get data flowing, we can open a terminal emulator to communicate with the ARM A72 processor, which is running Linux. The processor has booted the project containing the ILA from SD card and has now issued a command prompt. Switching to that card, then listing the contents, shows a number of applications that were also generated during the Vitis build. Running one of those applications starts data flowing in and out of the AI engine array, thereby triggering the ILA and showing activity on the previously inactive interfaces. This is a simple example of domain interaction. We'll consider cross-domain debugging in more detail later. Debugging across three domains can generate a lot of data. To address that, the hardware debug link has evolved. The physical portion of that link is your cable. The platform cable USB 2 provided a USB 2 to JTAG link. That evolved into the SmartLink cable, which added general purpose I/O plus an Ethernet port for remote debugging over a network. And now, to support the additional demands of debugging in a heterogeneous compute environment, the SmartLink Plus adds high-speed interconnects and additional capture memory. Here you see a table showing the evolution of the cable, and note the improvement in download times. This is essential for Versal debugging since a lot of data needs to be transferred, as we mentioned, both to configure and to debug the ACAP devices. Here we see a SmartLink Plus cable. On the host side, the Ethernet and the USB 3.0 for connections. A micro SD card for holding images. And on the target side, the GPIO, the JTAG, the high-speed debug port, and a parallel interface. In addition to the new SmartLink Plus cable, there are related enhancements in the Versal device, most notably the high-speed debug port in conjunction with the platform management controller. The high-speed debug port utilizes transceivers to carry debug data over high-speed links, running either the Aurora protocol or PCI Express. Typically, the Aurora serial links are used for cable-based debugging and the PCIe for data center card debugging. Axie4 streams link the different domains, and the platform management controller in the PS domain orchestrates debug traffic. The debug packet controller assists the PMC by assembling and disassembling packets to maintain the two-way debug traffic. The high-speed debug logic is implemented in the Versal part. It links to the SmartLink Plus cable with the parallel debug on the MICTOR38 connector, high-speed serial Aurora on the USB-C connector, and JTAG on the PC4 connector. The cable also has dedicated general-purpose I/O for board-level control and visibility. Host-side communication is over USB 3 and/or gigabit Ethernet. Also note that the SmartLink Plus has DDR4 trace memory up to 14 gigabytes and onboard debug logic. This integrated memory and logic enable the SmartLink Plus to capture debug information independently of the host, enabling debug sessions to be shared across multiple networked computers, even those using different versions of the development tools. This is a great feature for team-based remote hardware debugging. If you're designing your own board, then the VCK190 user guide, UG1366, shows the hardware setup for the high-speed debug port interface at the board level. For further details, you can reference the schematics for that board, which you can download from the VCK190 product page. The schematics are downloaded as a zip file, which contains a .dsn OrCAD schematic design. So now that we've discussed the new high-speed debug port and the SmartLink Plus cable, it's time to discuss the tools. Two aspects of the tools, that is, adding the ILA into your Versal design and running the debug tools. As you're probably aware, the Integrated Logic Analyzer is implemented in the PL domain. Adding the ILA effectively means instantiating one or more ILAs into the PL portion of the hardware design. Since our focus is debugging the AIE portion of a design, let's step back and review how a Versal design uses the AI engine array. Consulting the hardware manual AM009 for Versal core parts, there are three types of interface tiles that gate traffic in and out of the AI engine array: the PL interface tile, the configuration interface tile, and the NOC interface tile. The ILA can only capture data accessible within the PL fabric. For AIE debugging, this includes the PL interface tile data and the PL paths in the NOC interface tile. That is, traffic flowing between the PL and AIE can be captured, while traffic flowing directly between the NOC and the AIE cannot. To see this from another perspective, consider the AI engine array architecture. The three types of interface tiles are placed in a row across the bottom of the array. There is one configuration tile, regardless of the array size. That is how the PS domain, including the platform management controller and the ARM cores, interface the array for configuration, monitoring, and debugging. The remaining two types include PL interface and NOC interface tiles. The NOC tiles are a superset of the PL tiles, including a PL AIE interface as well as a NOC AIE interface. The number of each varies with device density. In a VC 1902, for instance, there are 400 AI engines arranged in 8 rows and 50 columns. The bottom row, not counted as part of the 400, has one configuration tile, 23 PL interface tiles, and 16 NOC interface tiles. The total is then 39 columns with interfaces between the PL and AIE, of which 16 also incorporate NOC AIE interfaces. The key point here is that most of the data flowing in and out of the AIE array in a typical design is between the PL and AIE domains and can be captured by the ILA. So what about the NOC data that cannot be captured directly? Consider a data path from the NOC into the AIE. To capture the data using the logic analyzer, you can temporarily reroute from the NOC through the PL and into the AIE. Once debugging is done, return the path to its original form. The same approach can be applied to data flowing in the other direction. So now that we've established that the ILA is a PL domain debugging tool that can capture data coming from and going to the AIE array, we'll move on to how the ILA is instantiated in your design. The most direct and probably already familiar means of adding the logic analyzer to your hardware design is instantiation into an IP integrator block diagram. For the Versal tool flow, that means you are adding the logic analyzer to the platform. To do that, open your platform's block diagram, then instantiate the ILA with Axis streaming interface from the IP catalog. This is probably the way you've worked with ChipScope in the past, but you will see differences in the core configuration. Most notably, the capture options have expanded from nets to nets and/or interfaces with a defined set of interface types. For AI engine interfaces, the proper interface type is Axis Streaming RTL domain. As always, you can specify the memory type and depth for storage and can utilize advanced options such as trigger in and out for coordinating trigger conditions across multiple ILAs. Graphically adding nets and interfaces for capture is straightforward, with the editor showing green checks to indicate valid signals for a selected ILA input. In this case, the ILA is set to capture one interface and one net. Automation is available to complete the connections, connecting the ILA to the proper clock domain and reset. The advantage of this approach is that it is intuitive. The disadvantage is that it can only capture signals that exist in the platform. Many of the signals of interest for AI engine operation are linked into the design later by Vitis and are thus not present in the platform. Still, this approach is useful for adding ILAs to monitor platform signals that influence AIE operations. Another way to add signals using Vivado is to generate an instance of the Axis streaming ILA from the IP catalog. You can then instantiate that instance in your RTL. This can be useful in debugging AI engines if the RTL code interfaces the AIE array. Both of these approaches, adding the ILA into the IP integrator block diagram and parameterizing an instance of the ILA core for instantiation in RTL, require modifying design source code. For a typical scenario where you wish to remove the test logic for code release, this adds a housekeeping step of removing the ILAs from the source code prior to rebuilding the released code. Now we'll run through some techniques for adding logic analyzer nets without modifying the design source. The first is, again, in the platform project, working in the IPI block diagram. Consider the same nets we previously connected to an ILA instance. The alternative approach is to mark the nets for debug, both the streaming Axis interface and the single net. Notice that a bug icon displays when you do this. This conveys the status of the net as documented in UG 908. Also notice that connection automation is suggested once you select nets for debug. This allows you to specify ILA options, including if these nets will be automatically added to an existing ILA instance or to a new instance. If you're working in Verilog or VHDL instead of the graphical environment, then you can select nets using the Mark Debug attribute in your code. Once nets are marked for debug, you can run the debug wizard in the synthesis portion of Vivado to set other ILA options. Now it's time to enter new territory and mark nets that are linked in by Vitis. These nets do not exist in the platform and cannot be selected for debug using methods we've already covered. Referencing UG 1393, the Vitis Unified Software Platform documentation, there is a three-step process to add downstream nets, including AIE array interfaces, to the ILA, with each step accomplished using V++ command line options. First, compile kernels with the -g debug option to generate a debug-capable .xo file for each kernel. Second, list the kernel interfaces that are valid for capture by the ILA. Third, add valid interfaces to the ILA using the Debug ChipScope option. Since these steps are key to debugging ILA interfaces, it's worth taking a minute to show them in action. For step 1, make sure the -g, or debug in its longer format, is specified when compiling kernels for debug. Here we see that option applied within the makefile for a specific kernel. A debug-enabled .xo file and associated report are generated for each kernel. If you're not sure if your kernels have debug enabled, then you can view the report and search for debug. With step 1 done, we move to step 2 and now list the debug ports available for each kernel. And using the wildcard pattern star.xo will return a list for all kernels. For step 3, any of the interfaces listed here in step 2 can be constrained to compile as ILA debug nets. To add additional interfaces, we can add lines as shown here. When specifying interfaces, you can explicitly list them or leave the interface portion unspecified, in which case all selected interfaces from that compute unit will be added. You may have noticed this tickle hook script. I'd like to give credit to a coworker, Ludovic Obel, AI engine specialist in France, for working out details of this technique and sharing his work. The point of the tickle hook script is when the Vitis tools read the configuration file we just built, it hooks this script, allowing you to specify ILA options. If you don't specify these options, you get the defaults, which may not be what you want for your analyzer. So we've covered quite a few ways to add the debug nets into your design. It all culminates in an LTX file, and now it's time to run the debug tools. To recap, we've established that the domains interact. The PMC configures and controls the AI engines. The ARM core applications control AIE data flow and data streams between the PL and AIE domains. The opening demo also illustrated a simple case of domain interaction around the ILA, in which we set the trigger condition, started the ILA, ran the PS domain application, then captured data as data streamed between the PL and AIE domains. To focus on debugging a specific area in your code, you can add a prompt to the PS application code to stop execution. Run the code up to that prompt, start the ILA, then resume execution to capture signal activity. For finer grain control over the PS application as it interacts with the AIE domain, you can replace the prompted stop with the Vitis software debugger running on hardware, using breakpoints and running stepping features in the debugger to execute iteratively while running the ILA. To show these approaches, let's look at an example application which loops 20 times, reading register values from AIE interfaces on each loop iteration. Suppose we suspected a problem in the 5th pass. Following the first approach discussed, we would add temporary test code to stop execution and prompt for user input as the 5th pass is about to start. I've set the ILA to trigger when the register at offset 0 is read from the first kernel. This corresponds to reg 0 as output to the console by the application. Note that the first reported register read does indeed match the value captured by the ILA. So now the 5th pass is about to start, so we can force a capture to note the current conditions Then restart the analyzer and resume execution. This captures the activity around the focus area of the code, providing useful data for debugging. An advantage of this approach is that it requires no changes to your tool flow. The disadvantage is that it requires modifications to source code, and any change to the area in code where you're focusing for the ILA capture will require additional code changes and compilations. The second approach we mentioned can achieve this without source code modifications. It does, however, require adding the Vitis Debugger to the tool flow. The Vitis Debugger can be launched from within the Vitis GUI or from the command line. UG 1076 provides detailed instructions for both. In this case, I'm working in a makefile flow, so I'll launch the debug from the command line. Once the debugger opens, set a breakpoint at the start of the loop. Launch the debug session, then run to the breakpoint and iteratively hit continue until the fifth loop iteration is about to start. That is the same point where the user prompt was inserted in the source code for the first approach. Now open Vivado and the ILA connected to the same hardware target. As before, set a trigger condition based on register reads, then start the analyzer. With Vitis and Vivado running side by side, continue in the debugger to run the fifth loop iteration, which triggers the ILA and captures the register read. We've now reached the same point using two different approaches, one requiring source code modification, but no changes to the tool flow, the other introducing the Vitis Debugger. I'm going to take advantage of the debugger now to show a few additional ways you can interact with the ILA. Since the loop under investigation performs 4 register reads on each pass, a breakpoint was previously set on the loop start. I'm going to add breakpoints on each register read, allowing ILA captures for every read instead of just the first register. Now, switching to the ILA, it's a good case to take advantage of the auto retrigger mode. This allows running through the register reads individually and capturing each read sequentially without having to rearm the analyzer. Another ILA feature that can be useful while debugging is the window option for the sample buffer. Since we're sampling 4 registers on each pass through the application loop, it makes sense to split the sample buffer 4 ways. And to accommodate 4 samples, increase the ILA sample depth. Back in the Vitis Debugger, remove or disable the breakpoints on each register read and leave the breakpoint on the loop start. This will allow all 4 reads to be completed without interruption, filling the windowed sample buffer in the ILA. The Vitis Debugger provides a detailed view of AI engine code execution. You can step at the source or assembly level, noting changes in AI engine processor register values. Combining this level of detail with the hardware inputs and outputs captured by the ILA as you step through the code provides insight that can help you isolate issues that were not exposed in simulation or emulation. If you want to learn more, then check out the list of referenced documents provided along with this video. Also, check out the Versal Custom Thin platform, one of the reference designs included in the Vitis Tutorials repository on GitHub. You can find it in the Developer Contributed section. The developers are 2 AMD coworkers, Bruno and Derek. This design is actually a well-thought-out environment to build Vitis projects including RTL, HLS, and AIE source code, working primarily in a makefile and scripted flow. The README file and notes provide guidance on how to enable the ILA when building this design for hardware. The default target is the VCK 190 board. To summarize, once you have a compiled system and are ready to run on your hardware, the ChipScope ILA can be a valuable tool to supplement your AIE and system debugging.